Hello. So today we're going to talk about probability in this unit. So probability is our mathematical language for uncertainty. Whether you're rolling a dice, assessing a medical test result, or deciding whether to carry an umbrella, probability guides our rational decisions. So in this video lecture, we'll learn what probability is, how it is calculated, and why it is important. Even though it sounds really abstract, it has real practical consequence in our everyday lives. So let's dive in. So as you can see in the outline, today we'll start with a formal definition of probability. And first we'll talk about the single outcome calculations. Then we'll move on to the more complex ones, and that's when we'll talk about the and the or rule. And then we will focus on some popular examples of how our intuitions can lead us astray, like the Linda problem. And we'll move then on to the idea of expected values, which tells us when a bet is fair and when it's not. We'll wrap up by exploring common fallacies and biases like gambler's fallacy, base rate neglect, and overconfidence, and discuss how to critically assess risk in the real world. So let's begin. Let's define probability first. To simply put, probability measures how often an event would occur in the long run if we repeated the same scenario over and over again. Mathematically, you can think of probability of an outcome of an event is equal to the number of ways the outcome can occur divided by total number of possible outcomes. So let's take an example here. For a fair six-sided die, for instance, there is one face showing 3 out of 6 faces. So the probability of getting 3 would be 1 over 6. Note that this formula relies on the assumption of equally likely outcomes, meaning that the dice is fair. If it is not, then we'll look into other advanced ways or tools, but that's not that's not what we will cover in this particular video lecture. We'll stick to fair dice conditions, coins, and card situations in this video lecture. Okay, so let's practice with an example here. A fair six-sided die, which has 6 possible outcomes, right? And they are 1 through 6. Let's calculate what is the probability of rolling exactly a 3. Remember the definition? It is number of different ways you can get that outcome, which is 3. And there's only one way of getting 3. So 1 divided by total number of possible outcomes, which is 6. So 1 over 6 would be the probability of exactly rolling a 3. What is the probability of rolling a 1? It's the same thing. So now let's look at another example. What is the probability of rolling an even number? Well, now there are different ways of getting an even number. A 2 is an even number, 4 is an even number, 6 is an even number. So the 3 different ways of getting an even number. So 3 divided by total number of possible outcomes is 6. So 3 by 6 would give you, what is it again? Yes, 1 by 2. And what is the probability of rolling a dice greater than 6? Well, it is 0, right? Now, I want to kind of focus on one simple thing here. I want you to be aware that the probability values can be expressed in multiple ways. And the most formal way is to represent the probability value between 0 and 1. 0 means there is 0 chance, 1 meaning there is 100% chance. Now, while probability is usually presented in zeros and ones, there's another uh, um, way you can present it, which is in percentages. So a probability is like out of 1, a percentage is out of 100. So if you say the probability is 0.5, you're saying the probability in percentages would be 50%. So just multiply it by 100, you'll get the percentage. So just be aware, sometimes it's easier to talk in percentages than in fractions or the probability values. And it's always good to convert the probability values given in one format into values that are more comfortable to you individually. So these kind of outcomes, like we're looking at just the probability of a single outcome, in such cases are called single outcome cases, and these are pretty simple. And you just look at the number of possible ways of getting that outcome divided by total number of possible outcomes. No further rules are required for this. In the next slide, we'll talk about more complex situations where you are interested in multiple outcomes. That's when the rules come into picture. Okay, now you are interested in multiple outcome situations where the questions you're asking are not just related to one outcome, but multiple outcomes. The multiple outcomes can be within the same event or across multiple events. Now, suppose I flip a coin twice. So these are multiple events. And want to know the probability of getting heads both the times, right? Then you apply the AND rule because each event is independent of the other, and the probability of getting heads or tails uh, the first time and also the second times are same because these two are independent events. Use the AND rule, and according to the AND rule, the probability of getting heads and tails consecutively is probability of getting heads times probability of getting tails. We know that the probability of getting heads anytime is 0.5, 1 by 2, and probability of getting tails is 0.5, 1 by 2. When you multiply these two, you get 1/4 or 0.25. Now, this is because these two are independent events. Now, if you ask a question related to an event with exclusive outcomes, for instance, the OR rule comes into picture. This is about mutually exclusive outcome events. So if you're interested in knowing the probability of rolling 1 or a 2 on a die, the two outcomes that cannot happen same time. So these are mutually exclusive outcomes of an event. What do you do? In such cases, you just add the individual outcomes. So the individual outcomes probability. So the probability of getting 1 and the probability of getting 2. The probability of getting 1 is 1 over 6. The probability of getting 2 is also 1 over 6. And you add these two, you get 2 over 6. 2 over 6 is 1/3. Okay. Or 0.33. Or you can apply the same thing to the flipping a coin situation, right? When you flip a coin, if you're interested in knowing the probability of getting either heads or tails, would be the same thing, where you are trying to compare the probability of mutually exclusive outcomes of an event. In that case, you have probability of getting heads plus probability of getting tails. Probability of getting heads is half. Probability of getting tails is half. When you add these two, you get 1. Why do you get 1? Well, it is 100% certain that you will get either one or the other, heads or tails. That's why the total probability would be equal to 1, which is 100%. So again, the independent means is one event doesn't affect the other, and mutually exclusive outcome means that both outcomes cannot happen at the same time in a given event. So you might think that these simple examples are more abstract and they don't apply to our real life situations. But misapplying these rules that you've just learned can have serious consequences in the real world. For example, in medicine, miscalculating the probability of a false positive, meaning the probability of misdiagnosing a person as having a condition even though he doesn't, can lead to unnecessary treatments. In finances, for instance, misunderstanding joint probabilities can lead to, well, catastrophic events like portfolio losses. In jury trials, misusing probability can sway decisions on guilt or innocence. So that's why we must master these rules and be aware of when our gut feeling can mislead us. Let's look at an example for this one. Okay, so let's take an example of conjunction error. It's called the Linda problem. Here's the scenario. Linda is described as politically active, philosophy major student concerned with social justice. Now, you're asked to predict the likelihood for future career, and you're asked this question, or future life. You're asked to rank the following statements about Linda, right, in terms of likelihood or probability. So it has to be between 0 and 1, or percentage. Number 1, Linda is a bank teller. What is the likelihood of this? Number 2, Linda is a bank teller and active in the feminist movement. What is the likelihood of this? Take a pause, answer this. Okay. Many people rate the second option as more probable because it fits the story better. But that's impossible, right? The probability of two events being both true, probability of getting both heads and tails, right? Or probability of having two things like conjunction should be less than the probability of the individual events or outcomes of the events. So basically, probability of A and B should be less than or equal to probability of A multiplied by probability of B. This is called the conjunction error. And this is driven by the heuristic, the rule of thumb called the representativeness heuristic, which is this representativeness heuristic is a tendency to judge probability by how much something seems to match our worldview or stereotypes. Okay, so let's talk about expected value. So expected values give us a way to decide if a gamble is worth taking. Expected value is the average payoff you would expect if you played the game many times. You calculate it by multiplying each outcome by its probability and sum all it up. For example, if you win a $2 lottery with a probability of 0.5 and lose $1 lottery with a probability of 0.5, then the expected value would be 0.5 times 2 plus 0.5 times -1, which would be equal to 0.5. And it's positive. So a positive expected value means that the bet is favorable in the long run. A negative expected value means that you're expected to lose money over the long run. So use the expected values. But keep in mind that people usually don't care about the expected values, but they care more about their perceptions of loss and risk. That's why the fallacies. So as we discussed in the earlier slide, we said that people need to use expected values and loss of probability to actually make judgments that are rational. But the problem is that our perceptions of probability and the actual probabilities are different, meaning our perceptions of the expected values and the actual ones are different. So in practice, people often misestimate the probabilities. Think about lotteries. People pick lucky numbers or birthdays, convinced it will improve their odds, even though all combinations are equally likely. So every ticket has the same teeny chance of winning, very teeny chance of winning. That mismatch between perceived probability and the actual probability is why lotteries are sometimes called a voluntary tax on misunderstanding risks. We are not good at understanding risks. So let's look at some fallacies of probability. There are several classic fallacies to watch out for, but let's look at some classic ones. Gambler's fallacy. Gambler's fallacy is believing that after a long run of reds on the roulette wheel, black is due. In reality, each spin is equally likely independent. So the other one is the base rate neglect, where you focus on specific evidence like positive medical tests while ignoring how rare the disease actually is. Then there is a third one, which people are not good at understanding, which is the regression to mean. Assuming that an extreme performance, say an outstanding basketball performance by a player, will be followed by an even better one. When statistically speaking, that's not the case. An extremely outstanding performance would be followed by less than outstanding performance or even less than average, so that the overall average over time would be regressing towards mean. That's why it's called regression to mean. Now, we said that we are not good at risk assessments. Let's look at an example to illustrate that. So let's apply this to some real life examples. For instance, tell me if driving is more dangerous than flying. Statistically speaking, yes, driving is more dangerous, but flying feels riskier because plane crashes are vivid and they're dramatic, and also they are shown more on television than the other. Now, coming to vaccines, the chance of severe side effects is vanishingly small compared to the disease risks they prevent. So to compare properly, one thing you can do is to convert the raw numbers into likelihoods, or to convert the raw numbers like deaths per million miles driven or shots administered into some more concrete values that you're good at thinking in. It could be probability values or percentage values. Then use the rules that we have learned to make your assessments of risk more closer to reality. So as we discussed in the hypothesis testing or unit, we talked about the p-values, right? So probability is an important construct that also underlies the statistical tests like t-test, p-test, f-test, not p-test, sorry, f-test that you may have learned. When you see a p-value, what you're looking at is the probability of obtaining the data at least as extreme as yours, assuming no true effect exists. So make sure that you read, not misread the p-values. Don't ignore the sample sizes or overemphasize the teeny but statistical significant effects. All these can lead to bad conclusions. Always ask, how big is the effect? How large was the sample? What is the real world context? So we looked at formal fallacies, but beyond formal fallacies, psychological factors can also skew our perception of risk. Let's look at a few examples. Voluntary versus involuntary. We accept voluntary risk like skiing, but we fear involuntary ones like air pollution. Natural or artificial. Natural hazards feel safer even when they're objectively riskier. Vividness. Well, dramatic events capture our attention. Feeling in control lowers perceived risk. Feeling in control like driving yourself. Familiarity. Familiar risks, even if deadly, are often underestimated. Recognizing these biases help us step back. Again, critical thinking. slow down, step back, and reevaluate the risk, and this time more rationally. Okay, to sum up, here are the key lessons. Use the formal probability rules rather than your gut feelings. Master the rules like and, or rules, and the expected values to make sound decisions. Watch out for common fallacies like gambler's fallacy, conjunction error, base rate neglect, and always critically evaluate statistical claims and perceived risks. I hope you like this video. Thank you.